Hello, students. Welcome to Fatigue Analysis. I'm Dr. Stewart. Today, we're going to do an example for notches with fatigue. In the example we're doing today, a short crack grows from a notched plate. We're asked to determine the fatigue life given certain information about the notched plate. We're told that the plate is a infinite width plate with a center hole that has a notch on it, and it's a double-sided notch in the center of this plate, and we're given the dimensions that the plate has. We're also given a nominal stress range for the fatigue cycle. We're given an initial crack length size. We're given the static stress concentration factor, Paris law constants, and we're told of the critical crack length at which failure will occur. With the diagram that we're given of the specimen, we're also given a plot of the stress intensity factors. And in this diagram, we find that there are two equations. There is the stress intensity factor when the initial crack length is very small, K small, right? And it has a certain relationship with stress and stress intensity. And then there is the K factor for if we had a long crack within the body, where in the case of the long crack, the effect of the notch is no longer present, so we're not using a KT or KF factor inside of the equation. So these are the two options that we have. And our goal is to determine the fatigue life, and we're going to have to take into account both K small for when the crack is very small or very short to the crack growing very long. In order to do that, we're going to need to split the linear elastic fracture mechanics approach into two parts. A part for the short crack up to the transition crack length, and then switch over to the portion for the long crack until rupture occurs. So let's go about solving this problem. And we're going to solve this one symbolically. So we're not going to actually put numbers in, but we're going to go through what is a procedure. The first step is we need to find the stress intensity factor equations specific to our geometry and loading condition. In our case, those equations are given in the plot. We're given the equation for the short/small crack, and we're given the equation for the long. So we're going to program those equations here into MathCAD, defining that we're going to have 1.1 times the KT times the net stress times the square root of pi times A, where A is the crack length. So this is a K short, and then this is L for K long. In the long case, you see that KT is not present. That means the crack is long enough that we're outside of the stress field and the stress concentration of the notch, so there's no KT. All right. So now that we've got those equations established, we then need to find the transition length at which our specimen can be said to switch from the short crack behavior to the long crack behavior. How do we do that? Well, what we do is we set K small equal to KT, and then we solve for the A that will get us that'll hold this equation true. When we do that, we can rearrange and we'll find that transition crack length, or let's say solve for .at for the transition length, we'll find that A dot T for this equation is equal to R divided by 1.12 times KT, all of that squared, minus 1. Now, in other problems, we may not have the same stress field equations. Ks and KL are going to be different. So we're going to need to get comfortable with rearranging and solving, setting those two equations equal to each other and rearranging and solving. Once we've found our AT, our transition length, we then can go about applying Paris's law to finding the cycles to failure. where if we take Paris's law and rearrange it, and if we split it into a portion for the short and the long crack, we get the following relationship, where the cycle to failures is equal to the definite integration of 1 over c times delta ks to the power m plus the integral, the definite integral of 1 divided by c times delta KL to the power m, right? And both of these are going to be integrated over their respective ranges. So for the short crack, we're going to integrate from the initial value to the transition length. And then for a long crack, from the transition length to the final or the critical crack length, we're going to integrate. When we complete this integration, putting our real numbers in, we'll end up with a measure of the cycles to failure that takes into account both the crack growth rates in the short regime as well as the crack growth rates in the remaining long crack regime. All right, so I think we've got a pretty good summary of this problem. We solve this problem symbolically, but it would be as easy as modifying what we have here and putting numerical values into this. So say this was a 15 KSI. Simply plugging in those values, we can find an exact solution to this type of problem. All right, so I'm not going to take up any more of your time. Thank you for watching the video. Please hit the subscribe button so you can get the new lecture videos and example videos that are coming in this fatigue analysis class. Also hit the bell so you can get notified on your phone or in an email when new videos are uploaded. All right, I'll see you in the next video.